colleagues and friends. Welcome to our today's PCS IBS seminar. It is a pleasure to host and have with us here today Professor Tomi Ohtsuki from Sophia University in Tokyo. And our scientific host today is Alexei, who will introduce Tomi.
Yeah, okay. Yeah, thank you, Helen. So let me briefly introduce you our today's speaker, Tomi Ohtsuki from the university. So he received his PhD from the University of Tokyo in '89. He's now a full professor at Sophia University in Tokyo. And his research interests center around theoretical condensed matter and computational aspects and methods, including transport properties under the physics of localization and quantum Hall physics, and also recently many deep learning and machine learning techniques. And today he's going to talk about Anderson physics and non-Hermitian systems. So yeah. This, please. Yeah, let's welcome the speaker, and the screen is all yours.
Yeah. First, I'd like to thank Alexei and Barbara for inviting me to this nice institute. The topic I'm going to talk about is mostly the Anderson transition in non-Hermitian system, which have 38 symmetry classes. And what I'm going to talk about is that this new 38 symmetry classes of non-Hermitian systems can be mapped to 10 Hermitian symmetry classes. So we don't need to calculate anything new for non-Hermitian systems. That's what I'm going to talk about. And if I have time, I will also comment on the energy level statistics and singular value statistics in non-Hermitian systems. But first, let me begin with this statistics. This is the year and the number of publications and number of citations, which includes non-Hermitian in the title of the paper. So around 2017, the number of papers are increasing rapidly.
Tomi, what was the first one in 1967?
That I don't know. Around here, here is the Hatano-Nelson model. 1967, I don't know. 1996 is Hatano-Nelson, but it didn't catch many interest. But now the number of publications are increasing, partly because of the topological things. Non-Hermitian physics also shows topological transition. And that is why the number of papers suddenly increased around 2017. Okay, so the outline of my talk is that I will first explain that there are 10 Hermitian symmetry classes, whereas we have, which is extended to 38 in if we allow non-Hermiticity to the Hamiltonian. And critical behavior, that is the localization-delocalization transition, changes when we add non-Hermiticity to the Hermitian system. But a correspondence exists between 10 Hermitian and 38 Hermitian universality classes, leading to what's called superuniversality. Superuniversality is that different symmetry classes show the same critical behavior. And as you know, 38 is greater than 10. So there should be superuniversality if this mapping is correct. And then if I have time, I will talk about the level statistics and the singular value statistics. But anyway, let me begin. Let me persuade you that this correspondence is correct. Here are 38 non-Hermitian symmetry classes. And here are well-known 10 yes, 10 Hermitian symmetry classes. And these are the correspondence. And as you know, one Hermitian symmetry class have 1, 2, 3, for example, 1, 2, 3, 4, 5 counterparts. So these 5 classes leading to the same symmetry class of Hermitian system share the same critical behavior. And that's why I say superuniversality.
So this is in terms of only critical behavior. But
Yeah, only, well, critical behavior and topological behavior are the same. Okay, this mapping also works for the topological property. So there is, for example, this one and this one, A3 and A3 plus S minus, have the same topological property because it's mapped to the same class. So the wave function, the things related to wave function amplitude are described by this one.
What is the meaning of the color?
Oh, yes. These blue lines have less symmetry. So there aren't any symmetry here except sublattice symmetry, the blue line. And these have a single symmetry, time reversal symmetry. And here we have 2 symmetries, and we have 3 symmetries there. But, you know, even with 4 symmetries, sometimes it's reduced to the most general class A. So it's not so trivial. Fitch symmetry class goes to Fitch. But thanks for the question. The color indicates the number of symmetry in the non-Hermitian system.
Yeah, so for example, in like Stano-Nelson, it's like one dimension, no symmetry, but still there is a bulk on the corresponding
right.
non-Hermitian scheme. So what is the Hermitian counterpart? You double.
Yes, I will explain it later. So this is a conclusion, and I'm going to explain why we have this correspondence.
Does the one-dimensional systems are there somehow presented in this?
Right, yeah.
Okay.
Even one dimension, for example, non-Hermitian Hatano-Nelson model have critical behavior with critical exponent 1. And it is mapped to class BD1. And in one dimension, class BD1 also shows exponent mu equals 1.
And SSH, for example.
Yeah. Yeah. Okay, let me proceed.
Only is a single letter in one particle.
It's a one, no, yes, it's a Hamiltonian symmetry. So even for many body system, we can use this one. Right. This is just a symmetry of the Hamiltonian. So if you write down the many body Hamiltonian and identify the symmetry, identify the symmetry of the non-Hermitian Hamiltonian, and then you can predict which symmetry class that the system belongs to. Okay, what I'm going to discuss is a critical exponent nu, which describes the divergence of the localization lengths from the localized space or insulator phase towards the critical point. We can also discuss from the metal side, but I will focus on the localization lengths from which diverges toward the critical point with exponent nu. And you know, the conductivity exponent S is related to nu, so nu only determines the universality. Okay, let me begin with the Hermitian case. we don't, I'm going to discuss the random system. So we don't have any translational or rotational or parity invariance due to randomness. So what is important in this system is a time reversal, particle Hall, as well as sublattice symmetry. And these Hermitian matrices are random Hermitian matrices are classified to 10 classes. 3 of them are Wigner-Dyson. 3 of them are Gade-Wegener. And the other 4 are Bogoliubov-Dugen classes. And we can summarize the 10 classes as follows. And class A, the most general one. No time reversal symmetry, no particle Hall symmetry, no sublattice symmetry. Correspond to class A. And if we add time reversal symmetry plus time reversal symmetry minus. Plus and minus is correspond to whether this unitary matrix P is symmetric or antisymmetric. So we have 3 possibilities. Time reversal symmetry is absent, plus 1 or minus 1, so 3 possibilities. So is the particle Hall symmetry. So 3 by 3 is 9. But even without any particle Hall symmetry, there are possibilities that there is a sublattice symmetry. So we need to add 1. So 9 plus 1 is 10, and that completes the classification of the Hermitian random matrices. Okay, and these are the result of the critical exponent, and the first 3 of them are estimated by one of the audience, Keith Sledin and myself, for 3 Wigner-Dyson classes. And the other classes are recently estimated with by Tom Wang and Liu Shindo and myself. And class D3 is estimated by other guy. And but what I want to emphasize is that depending on the symmetry class, the exponent changes.
What does mean in chiral symplectic case this no information or
yeah. Well, yeah. Yeah. Okay. Having this in mind, we go to non-Hermitian system. So I said time reversal symmetry, which is written as follows, where H is related to H transpose by unitary matrix P. This is time reversal symmetry. But since in the case of Hermitian, H transpose is equal to H conjugate. So they are the same symmetry. But in non-Hermitian system, this symmetry can be different. So the time reversal symmetry is double. So is the particle Hall symmetry. Particle Hall symmetry can be written as this, but this H transpose and H conjugate can be different in non-Hermitian system. So these symmetries are double and resulting in 38 symmetric classes. And yes,
You can have both symmetries.
if I have both symmetry, then this becomes Hermitian. So
So we'll have one or the other.
yeah, one or the other, or none. And we also have some chiral symmetry. And our experience for the Hermitian system is that each 10 symmetric classes shows a different critical behavior. So naively thinking, we expect that 38 different symmetry classes shows different critical exponent. But that is not the case. Because, let me explain, let me give you some example of non-Hermitian system, or symmetry of the non-Hermitian system. First, this is a well-known Hatano-Nelson model, where we have asymmetric transfer from I to I plus 1 and I plus 1 to I. So the magnitude of T plus and T minus are different. And we can gauge out the phase, and VI is a random potential which is positive. And then the Hamiltonian is a real matrix. So H equals H star, H conjugate. But due to the difference between T plus and T minus, H is not equal to H transpose. So this we call non-Hermitian class A1. The other case is that H isn't equal to H conjugate, but H is equal to H transpose, which I'm going to explain. It is a non-Hermitian model where the non-Hermiticity is introduced in the site potential. That is, site potential is now imaginary. We have this imaginary part of the potential. But if this theta is there, I mean, if there aren't any parallel space, this part is symmetric. So the Hamiltonian is symmetric if theta is zero. But it is not equal to H conjugate because of this non-Hermiticity. And this we call non-Hermitian plus A1 dagger. And if this is not zero, but if this part, fire space is not zero, it's called U1 model, and the Hamiltonian belongs to non-Hermitian plus A1. Non-Hermitian plus A is the most general one, where there are no symmetry.
Yes, are there any classes associated with just the scheme and the fed systems?
Yes.
Yeah, but I mean, there's an on-site disorder, but I'm curious, I mean, in principle, you have a localization that would be zero.
Yes.
Is that still following one of the classes?
Yeah, the Hatano-Nelson have scheme effect.
Yes.
But we don't need the asymmetry of the whole. But it's possible that skin effect appears even in this site potential model. Yes.
The major part of the site potential is also random.
Yes, thanks for asking. These W and WR and WI can be random. Okay, and let me ask one question. Does this non-Hermitian plus A1 dagger shows different critical behavior from the Hermitian A1? And the answer is yes, the exponent changes. I say the universality class can be mapped, but I said exponent changes. You might, and I will explain why. So for this study, I use transfer matrix. Transfer matrix relates the wave function on the ith layer to I plus 1's layer. Psi I plus 1 is a vector which has whose components are the wave function amplitude on the I plus 1's layer, which is related to psi I, the wave function on ith layer, and psi I minus 1, wave function on I minus 1's layer. via transfer matrix MY. It depends on which site we are focusing on, because HI is random and depends on the number of the layer or index of the layer. And MY is multiplied to get M, which is the wave function here, and the wave function at LZ. And we define omega as log of MM dagger and obtain the eigenvalue of this divided by 2LZ to obtain the Lyapunov exponent gamma. It's rather technical, so if you are not interested in it, you can forget about this. But this gamma, the Lyapunov exponent, or inverse of the smallest positive Lyapunov exponent, correspond to the inverse of the localization length. And this localization length is the localization length along the bar, which is normalized by the size of the cross-section to define the non-dimensional scaling value. In the case of Hermitian case,
I have a question.
Yes.
So, how about we consider the M minus 1, like our minus 1?
M minus 1.
The inverse of M, it is in
Yes, we start with the unit matrix or unit vector and multiply many times to shuffle the initial vector. Is this your question?
I mean, here you can consider the M run from the left to the right, but you can here consider the M run from the right to the left.
You mean this to the... Yes, actually we get the same Lyapunov exponent. If the system is reciprocal. I mean, I talked about Hamiltonian model. And in this model, the Lyapunov exponent depends on the direction. Thanks for asking. But here, I won't show the case of Hamiltonian, but was a reciprocal model where right going and left going gives the same result. And here is the transfer matrix properties for Hermitian case, where we have plus Lyapunov exponent and minus Lyapunov exponent appears in pair. And even in the case of non-Hermitian system, for example, non-Hermitian plus A1 dagger have this symmetry for transfer matrix. And the plus and minus symmetry remains, even in the case of non-Hermitian system. So this is one way to check the numerical calculation. Another thing is a scattering matrix. In here, the current comes in from 1 and 3 and goes out from 2 and 4. So channel 1 and 3 are related to 2 and 4 by S matrix. And this S matrix is unitary in the Hermitian case, but it's not unitary in the non-Hermitian system. But fortunately, S dagger of H is equal to S inverse of, not H, but H dagger. And since H and H dagger are different in non-Hermitian system, S dagger is not the inverse of S, So this relation, R dagger R plus T dagger T equals unit matrix doesn't apply for a non-Hermitian system. But R dagger of H times R of H dagger plus T dagger of H times T of H dagger should be a unique model. And this relation also is checked numerically to monitor whether the numerical calculation is okay or not. And here are the summary of the Lyapunov exponent and conductors. So even in the, I just want to say in this slide that there are some relation for Lyapunov exponent as well as the two-terminal conductors remains even in the non-Hermitian system. With this in mind, we did the numerical calculation. We obtained the smallest positive Lyapunov exponent, which is the inverse of the localization length, divided by the width of the cross section, which is a scaling variable, and we plot them by changing the system size. So the gradual curve is for system size 6, and rapidly changing curves are system size 24. And we have this common cluster here, which indicates the transition. And here is the phase diagram. WR is the random real part of the random potential, and WI is the imaginary part of the random potential. Imaginary part of the random potential was the width of the random potential distribution, I should say. And here we changed along this line where the value of the strengths of the real and imaginary random potentials are the same. Now let me tell you what and these circles are the numerical data. It's not like this, but rather like this. One might guess that WR squared and WI squared, square root of WR squared and WI squared will determine the strength of the random potential. But it is not the case. It doesn't, the phase diagram is not like this, but goes like this.
So, but when Wi equal to 0, why Wi equal to?
Wi equals 0 is Hermitian.
Yeah.
Hermitian Anderson transition.
So why is different from this?
This one is here. So the critical point is here.
Okay.
6.3. The reason why I chose this line is as follows. This is the numerical data. And this is the schematic of the renormalization group flow. Yes, sir.
So, is there any difference in this critical behavior for left and right eigenstates or the localization?
Yes, I'm mainly focusing on the right eigenvector, but right and left behaves almost the same in the sense of the localization length.
Okay, so the exponent is same.
Yeah.
So, what parameter is changed here in order to obtain this loss?
You mean this is at the band center, and this is away from the band center.
Yes, but the normalization group flow is when you change something. What do you change here?
You mean why it changes? I mean the RG flow changes because at E equals 0 there is a symmetry between WR and WI. So the critical behavior or the localization length becomes the same if we interchange WI and WI, WR and WI. Just at the band center, we can prove that the localization lengths are the same if we interchange WR and WI. And in fact, the critical exponent where the real part of the random potential is zero, and only the potential is pure imaginary. There appears a fixed point, which is exactly the same as in the real potential Anderson transition. So this point, this critical fixed point and this fixed point are the same. But this is an artifact of band center. And away from the band center, this fixed point disappears because we don't have any symmetry. Did I persuade you?
I meant something else. You probably can formulate it. When you discuss the normalization of your parameters, usually you should change something. For example, scale on which you look at your system. The question was, what quantity do you change in order to obtain this flow of parameters W? You perform some decimation of movements or something like that.
Okay, what I can say is that if we start from here, and after renormalization, the non-hermiticity becomes larger and larger. So non-hermiticity is a relevant perturbation. So if we start with this and we use the RG procedure by dissipation, then the WR increases, WI increases. So this is the Anderson transition, and this is the standard Hermitian Anderson transition. But once we have imaginary potential, then it goes away from this fixed point. And if we are close enough, we can fix the behavior of the new fixed point FP3. And more generally, it looks like this. And these points correspond to Hermitian orthogonal class fixed point. And just it's quite easy to prove that at energy equals zero, this phase diagram becomes symmetric.
I have energy
Yes.
means the major party is zero, or only near party is zero.
Sorry?
Energy equals zero means complex. There is the non-Hermitian system complex eigenvalue.
Oh, yes. We have complex eigenvalue, but let me think. This can be complex. The energy can be complex. I will explain it to you later, because as you correctly pointed out, this energy, which energy region we are considering, it sometimes becomes very important to discuss the critical behavior. Yes?
So do I understand it correctly that to see this RG flow, essentially you are looking at the localization length at a particular energy and how it depends on these parameters Wi and WR.
Right.
And then you are looking at how it flows as we change the parameters.
Right. Exactly.
I can what is the spectral around this localization. So first region is some eigenstated crossover or
Eigenstate of
eigen energy.
The
crossing over the.
I'm fixing the energy and changing the strength of the random potential.
But this kind of fixed point is related to the phase transition.
Sometimes.
Yeah, but how to understand it? Fixed point of two different randomness. What difference in left and right side random?
I'm not sure I understand.
What is it? FP1 and FP2, what is the difference?
You mean FT?
One state.
Yeah. You mean
You follow the subline of blue line.
you mean blue line? Yeah.
This system is changed, right? The popular class is changed.
Yeah. You mean this critical line?
Yeah.
And your question is that if we start around here, it would normalize to there, right? Yeah.
You change the parameter. That you change.
Yeah. We are cutting. I have to say we have another direction, which is proportional to energy E. And that is why they look different. Yes, please.
So in the standard Anderson transition emission case, you have a field theory of the Anderson based on the non-linear signal.
Yeah.
With the standard RG procedure, which involves a partial summation of degrees of freedom in the field in the signal model, and then a rescaling of the length. Now, is there any similar theory for the non-Hermitian case, any similar type of field theory?
Not yet. I discussed it with my colleague, but not yet. But I'm sure we can describe this critical behavior by nonlinear sigma model. But usually we start with the conductance, Kubo formula conductance calculation, and take the retarded and advanced Green function pairs and reduce it to nonlinear sigma model. And this starting point is a bit non-trivial in the case of non-Hermitian system. We don't know whether the Kubo diagram is a good starting point to derive the nonlinear sigma model for non-Hermitian system. Yes?
These results are analytical or numerical?
This one is numerical.
No, these RG flows.
This RG flow is just schematic.
Okay.
Yeah. To be consistent with numerical calculation. Okay, this symmetry, it can be proved exactly. But other than that, it's just a conjecture consistent with mapping and consistent with the numerical calculation. Okay, and I'm running out of time, so this is the result of the scaling plot. And this is the case of non-Hermitian system given by Keith and myself. And they are, and this is a case for non-Hermitian class A Vandana, where the imaginary on-site random potential is introduced, and you say they are clearly different from each other. So non-Hermiticity changes the exponent from 1.57 to 1.19. But we can map the non-Hermitian system to Hermitian one by a technique called hermitization, originally invented by Feinberg and Z in 1997. Here, H is a non-Hermitian matrix. E is the energy we want to consider. And the hermitization is done by taking this block and this block separately with 0 on the diagonal. E star is a complex conjugation. H dagger is a Hermitian conjugate. And H tilde itself is now Hermitian. And the thing is that if we solve the eigenvalue problem for non-Hermitian matrix and obtain right eigenvector, and also if we obtain the left eigenvector by solving this. Now, this psi L star left eigenvector conjugate plus 0, or 0 and right eigenvector, are now the eigenvectors of Hermitized Hamiltonian H tilde with eigenenergy Z. So the property of the wave function of non-Hermitian system H with energy E is now mapped to the Hermitized Hamiltonian with eigenenergy Z. Yes?
So H tilde looks like a spiral.
Yes.
Does it matter?
It matters. I will explain it right in the next slide. How this chiral form matters in this mapping. But if the wave function decays with localization length psi, so does this H tilde. And that's why I say we can map the non-Hermitian system to Hermitian symmetric classes. But as Keith now pointed out, this is what's called chiral symmetry. So you might think that all the non-Hermitian system are mapped to 3 chiral classes. I said there are only 3 chiral classes in Hermitian system. And this has a chiral form. So that is symmetry. So that naively thinking, all the 38 classes seems to be mapped to 3 classes. But this is not true. First of all, it's not H, but E minus H determines the symmetry. And that is, even if H is non-Hermitian class A1, A1 is a real matrix, but not symmetric, like Hatano-Nelson. But non-Hermitian matrix has eigenenergy, which is complex. So if you consider the Anderson transition at energy in complex plane, then the system is not non-Hermitian class A1, but is regarded as non-Hermitian class A, because E is complex. So E minus H is no longer real. So we need to be careful about choosing A, because E destroys some of the symmetry of the Hamiltonian. And next point is that Hermitized Hamiltonian, as I said just before, has a chiral symmetry. I mean, this form always have this form. So one might think that, but if H has additional symmetry, like another chiral symmetry, so it's not only this Hermitized form, but if H itself has chiral symmetry, then this matrix can be block diagonalized as H prime and minus H prime. And they are the same matrix, but minus is here. So that the eigenvalues comes in pair, but the symmetry class is determined by H prime. And this H prime is, in this case, class A. So if we add symmetry to the Hamiltonian, non-Hermitian Hamiltonian, sometimes it block diagonalized, and the symmetry is lower if we map it to the Hermitian system. And that is why the class A3, which has chiral symmetry, is mapped to class A, where there aren't any symmetry. But if we start with A, non-Hermitian class A, is mapped to class A3, the chiral unitary class. That is why this mapping is non-trivial. And let me say that class A1 data, or maybe I talk about it in the next slide. A few consequences from this correspondence. First is that the Hatano-Nelson model is non-Hermitian class A1. A1 is real but non-symmetric. Now, it shows exponent nu equals 1, which is well known. One-dimensional Hermitian class BD1, chiral orthogonal class, shows exponent 1. And both of them shows nu equals 1, and they are not just a coincidence, but has a reason to be equal because of this map. It's because of this map. More non-trivial case is topological magnon system. Topological magnon system, the magnon number is not conserved. So, and it is described like volume of the J equation, where magnon wave function times Hermitian H is equal to sigma 3 times E phi. If we multiply sigma 3, and since sigma 3 and both sigma 3 and H are Hermitian, but they are not commutable. Yes.
So in the first case, each non-Hermitian mode correspond to the topological zero mode in BDI class.
You mean this class BD1?
Yeah.
Yeah. And that topological transition shows nu equals 1. And which is equal to Hatano-Nelson. And this is because of Hatano-Nelson is mapped to BD1, the topological chiral orthogonal class. So where was I? So sigma 3 times H, sigma 3 and H do not commute. And this becomes a non-Hermitian system. And in 2016, I and Beijing University group analyzed this system and showed that quantum magnon-Hall effect seems to be the same as the quantum Hall transition. And we didn't know why, but now we know that this is...
Sorry, what is quantum Hall transition? Well,
quantum Hall transition, I mean, quantum Hall effect where the wave function or the Chan number changes from one integer to the other. And the localization length diverges when the quantum Hall conductivity, sigma xy, changes from one integer to the other. And that is quantum Hall transition. And we know that this exponent and that exponent for quantum magnon-Hall effect and the exponent of quantum Hall transitions were similar. And we didn't know why. But now we know why. This Hamiltonian, sigma 3h multiplied by I, shows this symmetry, which is non-Hermitian class A3. And non-Hermitian class A3, non-Hermitian class A3 is mapped to class A, which is nothing but the quantum Hall symmetry class. So that is why the quantum magnon-Hall effect and the quantum Hall effect shows the same critical behavior. Another thing is about the three-dimensional light localization. Without loss and gain, it should be the same as Hermitian class A1, which shows nu equals 1.57, estimated by Keith. Now, if we introduce loss or gain to this light localization problem, then class A1 data is mapped to class C1 or Newhoff-Dujan class. and the exponent changes from 1.6 to 1.2. That is what we predict for the 3D light localization. And these are the summary of numerical calculation to support the correspondence. And I want to emphasize that not only the exponent, but the critical value of lambda c. Lambda c is the value of lambda at the critical point, which is thought to be universal, coincide with what we calculate for Hermitian system. Not only the exponent are the same, but this critical lambda c is the same for the Hermitian system.
So,
yes.
Remind us what capital lambda was.
Capital lambda is okay. Sorry. Capital lambda is about where the transition occurs. Above this capital lambda c, the system is meta or delocalized, and below it, below this critical value is localized. You can also say that from this capital lambda c is the limiting value, where the scaling comes from. Okay, I have only 10 minutes. And I hope I have succeeded in persuading you that the non-Hermitian system and Hermitian system share the same critical behavior. And the remaining 7 or 5 minutes, I will talk about other properties. That is, we have shown that there is a superuniversality for Anderson transition. But how about level statistics? This is the typical energy levels in complex plane, real part of energy and imaginary part of energy. And it's not our work, but different persons' work. That it is noticed that complex energy level statistics, I mean the distance between the complex energy, S, always is proportional to cubic. And class A, A1, A2, DC, A3, and A3 level all show the same energy level statistics. And I want to distinguish them. This is the kind of super universality, but it is too super, I have to say, that we can't distinguish the different symmetry class. So what we did is to focus, to look at the singular value. Singular value is in Hermitian system, singular value and eigenvalues are essentially the same. But in the case of non-Hermitian system, they behave differently. And the question is, can we distinguish class A, A1, A3, DC, A3, and A3 data from the statistics of singular values? And for this purpose, I will focus on this quantity, singular value spacing ratio, Rn. Now, S is not the spacing of energy, but S indicates the singular value, which is always positive or 0. And this is the distance between n and n plus 1 and n minus 1 and n. And if this, we take the minimum of this, of these two choices. This is singular value spacing ratio, Rn. Another things we focus on is the minimum value of this singular value. And again, we use the Hermitization, and we can derive that singular value joint probability density behaves like this, with beta the standard level repulsion index 0 or 1 to 4 for these classes, and alpha, the minimum, alpha determines the minimum value of the singular value, or distribution of the minimum value, singular value, minimum singular value, which, and alpha value is 0, 1, and 3, depending on the symmetry. Now, class A3 and A3 dagger is distinguished from the other classes. And A3 and A3 dagger, if we look at alpha, they behave differently. So we can distinguish A3 and A3 dagger from the other classes. And we can also distinguish A1 from other classes, but they A1 and A1 dagger and C shows the same critical, same level repulsion. But A1 and A1 dagger has a different alpha, so we can distinguish them. The remaining ensemble is A1 dagger and C. But don't worry, A1 dagger and C are different from each other if we look at the complex energy. So you don't need to worry. So by doing so, we can, and this is a numerical demonstration, A1, a singular value distribution. This is the case for level spacing ratio. And this is the case for minimum singular value distribution. I think I'm running out of time.
You can take 5 more minutes.
5 more minutes. So
If that's
I just want to comment that there are cases. There are among 38 non-Hermitian classes. There are 5 cases where we have the real eigenvalues whose number is proportional to square root of the matrix dimension. Also, some of the classes show the soft gap for the density of state. Now, the density of state in the non-Hermitian system looks like this. Can be decoupled to the density of state for a complex plane and the density of state at the real axis. This is an example of the density of state in, what is this? Class A1 and class A2. And class A2 shows a soft gap energy equals 0. Whereas we see a strong peak of imaginary part Z, which indicate that real eigenvalue exists for class A1. Whereas we have soft gap for class A2.
This is specific. You can say that generally.
Yeah, this conclusion is only for the random matrix. And we examined it for 2 or 3 cases of many-body Hamiltonian. And they are consistent with the random matrix model in the metal side. Okay, these the typical soft gaps in several non-Hermitian classes. And I said 5 of the 38 classes shows real eigenvalue. This is the number of real eigenvalues as a function of the square root of matrix dimension, which is on a single line. So the number of real eigenvalues are proportional, not to the matrix dimension, but the square root of matrix dimension. And this is a numerical, and once we, in these 5 classes, we have real eigenvalues. So we can do the standard level statistics among the real eigenvalues. And these are the statistics which are different from each other. Which are, 5 symmetry classes all have real eigenvalues, but their statistics are slightly different from each other. And this is Bose Hubbard model with Hatano-Nelson type asymmetric optic, and which shows the soft gap expected from the random matrix model. Also, the number of real eigenvalues. We have a lot of real eigenvalue system, and level spacing ratio in the ergodic phase. And this is the level spacing ratio in the localized phase. Follows what we expect from that. This is what we expect from the random matrix model.
In this case, you fix the filling function, or you can change the filling function.
Change. You mean the size?
No, I mean the ratio of the particle.
Ratio of HI. HI is changed. And for large HI, the system becomes random. And the level statistics becomes Poissonian. Whereas for small HI, it looks like this, which is consistent with the random matrix model.
Think about the large limit.
Yeah.
You dominate the localization. That case is
but system size only 16. So. Yeah, in the limit of large system, I don't know. But maybe all the states look like it, as you point out. Thanks. So this is a summary. I think I almost succeeded in persuading you that non-Hermitian Anderson transition is the same as Hermitian Anderson transition. But due to the complicated mapping, non-Hermiticity seems to change the critical exponent in a non-trivial way. And I didn't talk about it, but I think, but I haven't shown numerically so far, that wave functions are the same. So, and we know that at the Anderson transition, critical point, the wave functions are multifractal. And in some two-dimensional case, some transition shows the conformal invariance. Some wave functions are believed to show the conformal invariance. So I think non-Hermitian system also shows the same conformal invariance as in the non-Hermitian system. And the singular value and the real energy eigenvalue are also an interesting quantity to be investigated in the non-Hermitian system. Thank you for your attention.
Thank you, Tomi, for this excellent presentation.
So from your transformation from the non-Hermitian to Hermitian, basically you already proved that the localization collapsing the right eigenvector at the same point, right? Because your Hamiltonian, after transformation, your new Hamiltonian know both about left and the right.
So this unifying the Hermitian universality classes from the Anderson transition point of view, I understood. But you mentioned also the topological properties also the same. So I understand that if we like this eigenvalue topology, complex eigenvalue topology, which is responsible for the non-Hermitian skin effect, that can be understood from this Hermitian. by mapping to Hermitian systems. But what about the eigenspace topology or this modified one boundary correspondence people were discussing in generalizable logic?
Yeah, it's not so complicated, I have to say, because the wave function, okay, how shall I go back to? Okay, we can describe the topological phenomena in terms of Chern number or some winding number. But we are considering the random system. So mostly what we do now is that whether we have skin effect or the wave functions are localized on the surface or not. And this can be mapped to each other. And that's why I say if one non-Hermitian system have a surface state, so does the Hermitian system. And that is why I said there is one-to-one, many correspondence between non-Hermitian topological system and Hermitian topological system. So the logic is simply that the wave functions are on the surface one.
This is a one-dimensional thing or general dimensional thing? Can that be the same?
One-dimensional.
Your model is based on the general dimensional.
Yeah, this correspondence works for every dimension, and even for including the many-body effect.
Do we have any other questions from the audience?
So maybe sort of naive question. So similar type of symmetry classes were discussed in the context of Liouvilleans and so on. So you can also look at so it will be the same thing?
Yes, Liouvillean, if we add dimension, can be mapped to so the density matrix can be mapped to density vector.
Okay.
And for this density vector, the Liouvillean looks like a non-Hermitian Hamiltonian.
Okay.
So that mapping works. I mean, this mapping works also for Liouvillean case.
I see, but
although I didn't discuss the time dependence or dynamics.
right. Maybe then, like in the beginning, why were people separating the symmetries of non-Hermitian Hamiltonians and Liouvilleans? Was like, so according to your argument, from the beginning, you could map one to another, right?
Right.
So there is no difference between these two symmetries, you're saying, or these symmetry classifications?
I think so.
Okay.
Estimate follow the rule, trace conjugate and it's the tensor matrix eigenvalue is always your constraint.
Yeah, dynamics I don't know. People working in Liouvillean are more interested in dynamics. And this mapping is just for the eigenfunction.
But the eigenfunction is restricted to the constraint of the estimate. Estimate is not related.
Yeah.
I think it is complicated. Yeah.
Yeah, I'm just curious. So what if we try to get this statistics SOG for all the information classes compared to the statistics for Hermitian models?
Yeah, why I did singular burden?
No, I'm just curious because if you look at this statistics saying spectral statistics of singular SVB for Hermitian and non-Hermitian models. Apparently, you see this studies.
Yes, there are we can, we can distinguish several classes from a singular value, but a singular value also shows a superuniversality. That is some, let me, some I focused on only 7 or 8 classes, but 38 classes share same alpha and beta. In my paper, in this paper, all the 38 possibilities are listed, but it's too complicated, so I skipped. But you are right. 38 classes shows superuniversality, as you point out.
Yes, and then the matrix is really here, the subject of R.
So just to confirm with that. So if there's no, okay, no, not, but no new possibilities of like critical phenomena from the Hermitian system.
Yeah, that is a subtle point I have to say. I assume that there is only one universality class for each symmetry class.
Yeah.
But if you have several universality class or several fixed points in a single symmetry class, then this mapping is not trivial. And in fact, there may be that looking at this correspondence, there are 1 cases plus BD1. In Hermitian system, we have 2 different exponents, depending on whether this has topological things and this is a non-topological system. So even if the symmetry is the same, there are possibilities that we have 2 fixed points. So in a sense, there is a possibility that the non-Hermitian exponent corresponds to unknown new fixed point for the Hermitian system. And so the mapping is correct, but there may be some fixed point which we don't know so far.
Any other questions from the audience? Seems not, so then let us thank Tomi again.